Previous talk. My name is Matt Vidmar and I'm a lecturer in engineering management at the University of Edinburgh, and I'm absolutely delighted to be hosting today's event. We have Johan Daelman here from the floating turbine design at Thistle Wind Partners, which is developing two ScotWind offshore wind projects, the Ayr and Baldwin offshore wind farms. And this talk, really interesting ways, links to the talk that we've just heard earlier today from our colleagues at EMEC, who were talking about that project of expanding the offshore wind around Orkney Islands, and the fact that there will be potentially a need to up to 8,000 wind turbines if you're installing them at 15 megawatts per turbine, and you want to generate somewhere between 120 to 150 gigawatts of power. And quite a chilling reminder is that, of course, if you start in 2025, you only have 7,300 days to do that, and there was a lot of other little bits of math that basically tell you it's a very, very hard job. So this talk takes up from there and continues on in an even more promising direction. What if those wind turbines were actually slightly bigger? So can we design an 18, 25 megawatt wind turbine? Well, that's actually Johan's work, and we are delighted that he'll be here sharing it with us today. Johan, excite us about the bright future for offshore wind.
Thanks, Stu. Pleasure. Ladies and gentlemen, welcome. I would like, first of all, to thank the Orkney International Science Festival for giving me the opportunity to present and talk about a subject that has passionated me for the last 3 years. Excuse my accent, I come from France, so I'll do my best to be understandable. Wind is everywhere on our oceans. Renewable energy ready to harvest. But we couldn't build the right turbines until now. These structures float on the ocean surface. They could deliver up to 11 times more energy than the world needs. It's a potential solution to our energy crisis. But does this technology live up to its promises? To answer this question, let's dive into the world of floating wind energy. So over the course of the next hour, these are the 5 questions I will address. First of all, I would like to explain basic notions and provide you some orders of magnitude for you to be able to fully apprehend the context of energy production. Then, of course, I will talk about the floating wind technology. Where does it come from? How does it work? Don't worry, it's not rocket science, it's quite easy to understand. And then I will try to explain why we actually want them to float. At the end of that chapter, I hope you will be convinced, and I hope that the only question that will burn your lips is, why haven't we done it sooner? And finally, the question that everyone always ends up asking me when I speak a little bit too much about wind turbines is, how big can we go in terms of size and power? I will try to provide you some elements to answer that question. So first of all, let's talk about some order of magnitude. What is the difference between power and energy? You see, energy is a word we use in many different ways to describe the way we heat our homes, or the fuel we put in our cars, or even the mood of the day. Energy cannot be seen or felt except when it's transferred from one place to another, or from one form to another. Energy is what makes change happen. The unit of energy is a joule. Power, on the other hand, is the rate at which energy is transferred, again from one place to another, from one form to another. The unit of power is a watt. To explain it a bit differently, think of it as water flowing through a pipe. Power would be the rate of water flowing through the pipe, so in cubic meters per second, and energy would be the amount of water that would end up in a bucket, so the cubic meters. So if you want to relate power to energy, it's quite simple. Energy is So the volume of water in the bucket, it's simply the flow rate times the amount of time that the water has flown. So energy, which unit in joule, can also be expressed in terms of watt times seconds. In the domain of wind turbines, the scale is so big that we often use kilowatts or megawatts. And we tend to replace the seconds by hours, so I will often speak about megawatt hours. So just be careful, it's not megawatt per hour, it's megawatt times hour. So let's apply this new knowledge on a simple example. How much energy does a 10 megawatt wind turbine produce over the course of 1 year? So I'll give you a hint, there are 8,766 hours in a year, and on average a wind turbine produces half of the time. It doesn't always produce because you don't always have winds. So the calculation is quite simple. Here you multiply 10 megawatts, that equals 8,766 hours, and you divide it by 2 to obtain a little bit less than 44 megawatt hours. So how much energy does a typical UK household consume over a year? The best thing I can give you here is look at your electricity bill from last year. On average, according to Ofgem, your house typically consumes about 2.9 megawatt hours. So the natural question that comes here is, well, how many households can one wind turbine power? You just divide the energy production by the energy consumption, and you end up with a little bit less than 15,000 houses. So that means that with 10 megawatt wind turbines, you could essentially power the Orkney, every house in the Orkney. Now let's talk about big orders of magnitude. The global primary energy consumption is about 180 terawatts hours. So a tera, previously I was talking about megawatt, a tera is a million times bigger than a mega. The consumption of energy, all sources included, has exploded since the Industrial Revolution. The availability of energy has transformed the course of humanity. Not only have we unlocked new sources of energy, such as coal and oil, but also have we unlocked massive amounts of them. The demands for energy is growing across many countries as people get richer and population increase. This chart here shows the evolution of energy consumption as a percentage compared to the year before. So what we see here essentially is that for the last decade, the world has consumed more energy than the year before. There are 3 exceptions to this. In the 80s, in 2009, and in 2022. So the 2 first drops are coincident with economic crisis, and the third one, of course, is the COVID period. So the global energy consumption continues to grow, but it seems to be slowing down, averaging 1 to 2% per year. So where does that energy come from? Well, let's zoom in on the previous graph and on recent years. So this graph here shows the energy production broken down by fuel sources. Globally, the largest amount of energy comes from oil, coal, and gas. They account for more than 80% of our energy consumption. A little bit less than 20% come from low-carbon energy sources, including nuclear, and out of those 20%, only 10% came from renewable sources. To prevent severe climate change, we need to rapidly reduce our global greenhouse gas emissions. However, the using energy accounts for 3/4 of the greenhouse gas emissions worldwide. It's the largest driver for climate change. It also pollutes the air, and each year nearly 5 million of deaths can be attributed to air pollution. So it's quite clear, we need to shift away from fossil fuels to an energy mix dominated by low carbon sources. Luckily for us, we have an abundant source of clean, renewable and free energy, the sun. You see, each year Earth receives about 180 petawatt hours of energy through solar radiation. 30% of it is reflected back to space, but still we get about 120 petawatts absorbed by our atmosphere, our land and our oceans. So just to be clear, a petawatt is a 1 followed by 15 zero, so it's quite massive. Now what is the link between sun and wind? Well, as I said earlier, energy can be transformed from one form to another. Well, wind is just solar energy transformed into wind energy. How does that work? Well, the wind is caused by the Earth uneven heating by the sun's solar radiation. You see, the Earth's surface is made of different types of land and water. Earth or land absorbs and rejects heat much faster than water. So during the day, one example of this is the daily wind cycle. During the day, the land heats up faster, so the air above the land heats up, warms, expands and rises. The cold air above the sea rushes in to take place, and this generates wind, an onshore wind, meaning wind going from sea to shore. At night, that circle inverts. The land cools down faster than the sea, so the air above the sea warms up, expands and rises, and the cold air from the land rushes in to take place, and this generates an offshore wind, meaning wind going from shore to the sea. In the same way, on a much larger scale, the atmospheric winds that circle the Earth are created because the land near the Earth's equator is hotter than the land near the North Pole and the South Pole. And that wind energy is abundant. It's estimated that there is a potential for 600,000 terawatt-hours of wind energy. This is enough to cover, if we could capture all that energy, it would be enough to cover 26 times our electric consumption, and even about 3.5 times our primary energy use, including fuel, nuclear, hydraulic, gas and coal. Okay, so now that we have all these orders of magnitude in mind, let's look at the technology and how it works. Wind energy is a 1,000-year-old technology. The Persians already constructed windmills in the 7th century. Some of them are still operational, built in Ireland. The Dutch also constructed windmills in the 11th century. You can still, some of them are still in use today. And then technology kept on evolving until the stage it reached today, the one we all know, the upwind 3-bladed wind turbine with a horizontal axis, such as those you can see here. The technology kept on growing in terms of size and power. See, a Dutch windmill typically produces a few kilowatts, the maximum. Last week, the biggest wind turbine was installed. Its power is 16 megawatts. The rotor diameter is 260 meters, and the tip height is about 300 meters above sea level. So that's higher than the Eiffel Tower, for instance. So from onshore wind turbines, we went to offshore wind turbine. The first offshore wind turbine was installed in the early 90s in Denmark, in a few meters of water depth, very close to the shore. And then we kept on going deeper and deeper, further away from shore. First we used monopiles, such as the one you can see on the top right. And as we went deeper and deeper, we switched to jackets, structures, as you can see on the bottom right. The deepest jacket has been installed this year in nearly 60 meters of water depth. The issue is that beyond 16 meters of water depth, the material and installation cost become prohibitive. So engineers looked around and thought, well, the oil and gas industry is already using a floating platform. Can't we just put a wind turbine on top of one of those hollows and have a floating wind turbine? And that's what we did. So, how comes that a structure that is 300 meters tall, that weighs thousands of tons, can float? Well, the solution was even by Archimedes 2,300 years ago. The famous principle, a body totally or partially submerged in water experiences a vertical upward thrust equal to the weight of the water dislodged. So to make something float, you just need to make sure that the water displaced by that hull is equivalent, but that volume in water is of a mass equivalent to the mass of the structure itself. Okay, but how do we keep it from drifting in the ocean and washing up on our shores? Well, just like a boat, we use mooring lines and anchors. There are different types of mooring line arrangements and different types of anchors. The best type depends on the nature of the soil. And from there on, the process is quite similar to what you can find onshore. The wind energy, which is basically kinetic energy, is transformed by the turbine rotor into rotational mechanical energy. That energy is transferred to a generator or an electrical motor through a gearbox, which converts the mechanical energy into electrical energy. And that electrical energy is brought back to shore, first through a export cable, as you can see on the left, which is a floating cable which goes from the floating foundation to a fixed offshore substation, and from there on there's another export cable which exports the energy, which injects the energy into the grid. So this is quite straightforward, but the real question is, how do we keep those wind turbines vertical? You see, the difference with bottom fixed is that there's no rigid connection between the foundation and the seabed. So if you have winds coming from one direction and waves coming from the other direction, how do we prevent the whole structure to capsize? Well, this is a subject on which engineers have been working hard since decades, and they came up with many different solutions. So I'll try to explain in simple terms how we can stabilize the floating structure. There are basically three ways to stabilize something that is floating on the water. The first way is to use ballast. So here, the principle is to place a center of gravity as low as possible on the structure. It's basically the principle used by sailing boats using a keel. So this is a very heavy mass placed far below the hull of the ship. Another way to improve the stability of a floating object is to increase the surface in contact with the water, or what we call buoyancy. This is the principle used by catamarans. So the boats with the double hull, they get their stability from the fact that the surface in contact with the water is larger. And a third way to ensure stability, I couldn't find a better example than this one, unfortunately. It's the subsea mines. Here the idea is to submerge an object which has a positive buoyancy, so which wants to shoot up and float on the surface, and retain it with a mooring line. So you can intuitively feel that if you push on that subsea mine, it will always come back straight. Floating offshore wind uses either one or a combination of these three stabilization means. The engineers have come with a wide variety of floating foundation types, but they can all more or less be classified into four types. The first one, the most simple one, is the spar. The spar uses ballast. The spar is basically a hollow cylinder, as the one you can see in brown here, a long hollow cylinder in which we place a lot of weight at the bottom. So think of it as a bottle of water that you would throw in the water. If the bottle is empty, it will float horizontally, but if you pour a little bit of water in it, it will get straight again. It's a very simple design, very easy to manufacture, but the issue here is that as a wind turbine gets taller and heavier, the cylinder needs to be, the length of the cylinder has to increase. And at some point it reaches a length that exceeds the water depth. So it's not practical for, it cannot be used for every offshore sites. The second type is one we call the barge. The barge exploits the buoyancy effect to stabilize itself. The length and the width of the hull is significantly larger than the height, which is precisely what gives it its stability. The issue here is that it offers a large submerged surface to the waves. So the loads of waves, the efforts of the waves, will destabilize the structure and make it, if the waves are too strong, the structure will move a lot. But of course there are solutions to this. One example is something we call the moon pool. To understand better the piston effect, the idea is to put a hole basically in the middle of the structure, and if the wave is high at the exterior of the hull, hydrodynamics will make sure that the wave is low in the center of the moon pool. So because one side is high and the other side is low, those two forces will cancel each other. Another way to improve the stability of the structure is to place large flat steel plates at the keel of the floater, and it will increase the drag forces, preventing the floater to move too much up and down. The third type is what we call the semi-submersible. This hull uses a mix of ballast and buoyancy to get its stability. The design seeks to minimize the surface area exposed to the waves, but always maximizing the volume of the hull, which is what provides the buoyancy. Ideally, the external columns would be spheres, because a sphere maximizes the volume while minimizing the surface. But the sphere is very impractical, it's very difficult to manufacture, so engineers prefer to use cylinders. Typically, semi-submersibles are 3 or 4 outer cylinders connected to each other by braces. The size of the cylinder and the distance between them is what provides them is what determines their stability. It's not the easiest concept to manufacture, but it's fairly stable and it's easy to install. The fourth type is the tension leg platform, or also called TLP. That one only uses the tension of its mooring lines. The idea here is to use a positive buoyant hull, which is retained in submersion thanks to its tendons. So technically speaking, it doesn't really float. If you cut the tendons, the whole structure will shoot up and float on the surface. So this allows us to place as much as possible of the structure far below the sea level, where the forces of the wave is less. Also, since the structure doesn't owe its stability to the width and length of the hull, the dimensions can be reduced and optimized, which also reduces, of course, the cost of steel required, about the quantity of steel required to manufacture them. It's probably one of the most stable concepts, but the big issue here is that without the mooring lines, it's not stable. So it's very difficult to tow from the harbor where it's manufactured to the offshore wind site. And we haven't really quite found the solution to install them in an economical way yet. And then there are many other concepts that cannot really be classified in one of those categories. They're usually hybrids. They are a little bit of one and a little bit of the other. One example, for instance, here on the left, it's a spar, so it uses ballast. It uses ballast. But also, it's also a GLP because the lines are tensioned and also gets its stability from the tension in the lines. Other types also include the idea of putting 2 wind turbines on one single platform, or even using a vertical axis wind turbine. This enables to place the weight of the nacelle or the generator very low, which also improves the stability on the floating platform. However, lessons learned from the oil and gas industry has shown that the most simple concept is often the better. Still, it's important that the industry researches outside others. So if you ask me which one is best, I cannot really answer. It depends on many factors such as the sea and seabed conditions, type of winds in the area, the depth of the harbour where you're planning to construct them, the manufacturing facilities you have available, and the price of the materials. So talking about material, all of these concepts can be manufactured either in steel or concrete. For instance, famous Norwegian power producer, Equinor, has in 2017 used steel for one of its spar, and 3 years later decided to use concrete for another wind farm. There are 4 factors entering into the decision process for steel or concrete. The most obvious one, of course, is cost. Concrete is cheaper. For the same volume, concrete is much cheaper than steel, but because we need so much more concrete for a concrete hull, in the end the cost sometimes evens out. The other thing here is that the cost of steel tends to be very volatile and to evolve a lot, whereas the cost of concrete is pretty stable, so it's much more easy to predict the cost of a concrete foundation than it is for a steel foundation. The second factor is the supply chain. In certain countries, it's much more easy to procure concrete than steel. For instance, here in Scotland, it could be easier and cheaper to procure concrete. But again, the supply chain evolves quickly, so you always need to keep an eye on this. Third factor is the environmental impact. Steel is often better and more recycled than concrete. However, the industry is currently working hard to, is investigating opportunities to recycle concrete as well. It's not clear today whether the carbon footprint of concrete production is higher or not than steel. Fourth factor is the site conditions. Concrete tends to be more vulnerable to freeze than steel, so for very cold areas you might contest that. Let's look a little bit at the size of those structures. The first pilot projects installed in the last few years typically use 10 megawatt wind turbines, and the length and width of those foundations was typically in the range of 40 to 60 meters. The height typically in the range of 10 to 20 meters. But in the future, when we'll be using 15 or even more, or even bigger wind turbines, the size of those structures could exceed 100 by 100 meters horizontally and 30 meters vertically. Just to give you a sense of what those sizes represent, on the right here you can see a render of a 15 megawatt floating foundation placed in the middle of Copenhagen, and that's on the central plaza. I feel this image gives a really good idea of how big the structures can be. So now that we know how it's working, I'll try to explain why we actually want those wind turbines to be floating. You see, we already have bottom fixed offshore wind, so why suddenly do we want them to float? Well, the first reason, of course, is that floating offshore winds open new markets. Most of offshore wind is currently located in the North Sea, because the North Sea average depth is around 30 meters. It's perfect for bottom fixed. But many other countries don't have those shallow waters. So floating offshore wind unlocks markets such as the US, South Korea, Japan, or France. Floating wind also enables to optimize existing markets. Because it can be installed further away from shore, floating wind can exploit areas that are less constrained by other activities such as defense, fisheries, tourism, or even conservation areas. Floating offshore wind can also help decarbonize the oil and gas industry. Oil and gas rigs consume a massive amount of energy to extract the oil from the earth. And they're often located in areas where the depth is way too high for bottom fixed. I previously mentioned the wind developer Equinor. They recently opened a floating offshore wind farm of 11 turbines, 8 megawatts, to power 5 oil rigs in the Norwegian Sea. They say they can procure, but that offshore wind farm can procure 35% of the electricity required by those oil rigs. Floating offshore wind also enables us to capture more energy. 80% of the total ocean area is too deep for fixed foundation. Many deep water areas are also located far offshore, where wind resources are stronger than fixed offshore wind location. Floating offshore wind will also provide local economic benefits. Whereas typically bottom fixed offshore wind, those foundations are manufactured in countries where labor is cheap, typically Asia, and brought over to Europe to be installed. Often they don't even touch the ground of the European port, they're directly installed in the offshore side, so it doesn't create much value for the local harbours. Floating offshore wind, on the other hand, is way too heavy. Those structures cannot be towed from Asia to Europe, so they have to be manufactured locally. So floating will drive investments and create jobs in ports close to the farm area. For instance, here in Orkney, there's a plan to develop a harbour in Scapa Bay, a harbour that will be dedicated to the fabrication, to the assembly of floating foundations. Finally, floating offshore wind also helps reducing the visual impact of offshore winds because they can be installed much further from the coast. Here's an example of a visual representation how beyond 15 miles we nearly can't see anymore those wind turbines. Okay, so it's quite clear floating offshore wind is a very promising technology, but why haven't we done it before? The market for floating offshore wind will grow significantly over the next decades. The rate of growth for floating offshore wind projects will largely be determined by how quickly a few remaining barriers can be overcome. Floating offshore wind is more expensive than bottom fixed. But why? Well, it's essentially due to the fact that it's a new and largely unproven technology. And as with any new technology, the person that will value the money to construct it is scared and will simply apply very high reimbursement rates. So this is what happens in the floating offshore wind industry. We need to borrow a lot of money to construct those farms, and since it's not a proven technology, well, the rates are very high. But as with any other industry, the experience and economies of scale will bring those costs down. Another bottleneck is the supply chain and port infrastructure. Here in the UK, there is simply not enough ports with the right combination of quayside length, water depth, or storage space to support the simultaneous development of gigawatt-scale floating offshore wind projects. So there's a need to expand or create or to extend existing harbours. It's also important to build a competitive local supply chain to fully capture the benefits of offshore wind. Here is an example of what floating offshore wind requires as infrastructure. So you need about 30 hectares of key space to store the components of the floater and of the wind turbine. You need a protected area to store the foundations before assembling the wind turbine. You also need an infrastructure that enables you to load out the heavy floating structures, typically a steam plane or a dry dock. There are also a couple of key technological bottlenecks. Here I've taken the most famous bottleneck. It's the electrical cable that will export the energy from the floating foundations to the offshore substation. That component is quite unique in the sense that it's not really used by any other industry. It's a big electrical cable that will move a lot because the floating platform is moving, of course. So it will be subjected to a lot of fatigue issues. And unfortunately, other industries have not really investigated that technology because they didn't need it. So this is one of the key bottlenecks that the floating offshore wind industry has to unlock. We also need to improve the installation methods for those floating foundations. The oil and gas industry already knows how to install massive floating oil rigs, but they only do it for 1 or 2 platforms per farm. In offshore winds, we could have to install 50 to 60 of those structures in only one season, in a few months. So we don't know really how to do this yet. The most problematic case here is the installation of a PLE, for instance. We can't really tow them out in a floating position, so we probably will have to bring them to site on a large open deck carrier, and then use a floating crane to put them in the water. Another issue is the replacement of major components. Those wind turbines will, at some point or another, break down, and we will have to replace the blade, or the generator, or a gearbox, or an entire nacelle. So in bottom-fixed offshore winds, you can just reuse the same vessel you used to install the wind turbine in the first place, but in floating, it's different because those boats, which are jacket vessels, cannot put their legs, the water is too deep, so they cannot put down their legs and get their stability from their legs. So we either have to tow back those wind turbines onshore, or to shore to the harbor, to use an onshore crane, or we have to replace a component offshore. But we have no methodologies, no technical solution for that yet. Some companies are investigating the option to integrate cranes directly on top of the nacelle. Some others are looking at cranes that could crawl along the tower to lift the blade, for instance. And some others are also investigating the option to put a crane directly on the floater. So, finally, is there a limit to the size of the power of this wind turbine? This is a very difficult question. There is no real technical limit to what we can do. I mean, we can send helicopters to planet Mars, we can build towers that are a kilometer high. However, there is a limit to what we can construct in a financially viable way. Bigger turbines, they produce more, but of course they cost more to produce. So there's a limit at which the production does not, the energy produced and sold does not compensate the cost of fabrication. when designing a turbine, the starting point is the business plan. Is to say we need to estimate and compare expenses with incomes. The revenues of a wind turbine is dictated by the amount of energy the wind turbine can produce, and the expenses is driven by the size, namely the rotor diameter. So what's actually really important here is to be able to relate the power of a wind turbine to the size of its rotor. So I can't tell you if there is a size limit, but what I can try to explain you is how to relate power to the size of the rotor. The key principle governing the conversion of wind energy into electricity lies in the laws of fluid dynamics, and namely in the one famous principle, the principle of Bernoulli. I forgot to bring a piece of paper here, but I won't display the equation, it's scary. But it's very easy to understand. If you blow on the surface of a piece of paper will magically lift. And this is simply due to the fact that when you blow, the velocity of the air increases. And the principle is that if the velocity of the air increases, its pressure decreases. So above the sheet of paper, you have high velocity and low pressure. And below the sheet of paper, you have low velocity and high pressure. High pressure below, low pressure above. This creates a force that lifts the piece of paper. It's this principle that enable planes to fly. The cross-section of the wing of the plane is, is this one, this shape. So when the air particle, if two air particles hits the front of the blade at the same moment, one of them has to travel above the blade and the other below, and they will have to join at the same time at the tail of the blade. Because the travel path above the wing is longer, the upper particle will have to travel faster than the lower particle. So faster particle, lower pressure, then slower particle at the bottom, higher pressure. This creates a lift force. Well, a wind turbine is essentially a rotating plane. The cross-section of a wind turbine blade is the same as the cross-section of an airplane wing. Except that here the lift force, or the blade is oriented in such a way that the lift force is always perpendicular to the axis of rotation of the rotor. So this is what makes the rotor spin. This is the only equation I will give here in this talk. This equation relates the power production, the maximum power of a wind turbine, to the rotor diameter. I will explain a little bit. So P is the powers, equal to 1/2 the density of the air, times an efficiency factor, which I will explain later, times A, which is the rotor's swept area. Of course, the area of the disk is related to its diameter. So the equation area equals pi times radius squared. And V is the speed of the wind at the third power. So the first thing we can see from this equation is that the power of a wind turbine is proportional to the cube of the wind speed. Meaning that if the wind speed doubles, the power produced is multiplied by 8. So that's why it's so important to always search for the areas that have higher winds. Even a very small increase in wind speed makes a huge difference in terms of power production. Okay, a little bit about this factor here in the power coefficient. This is a coefficient that contains all the information about the aerodynamic efficiency of a rotor. A wind turbine cannot capture 100% of the energy contained in the wind, because if that would be true, there would be no winds. Would be no wind behind the wind turbine anymore, because if there was still wind behind the wind turbine, that wind would still carry some kinetic energy. But that cannot happen. So it can be proven mathematically and physically. There is a limit to the amount of energy you can extract from wind. It's called the Betz limit. It's more or less equal to 59.3%. So we'll just remember that a wind turbine cannot extract 100% of the energy in the wind. So let's use an example to apply this equation. If my boss asks me how much will a 15 megawatt wind turbine cost, the first thing I will do is I will try to estimate the size of the rotor, because if I know the size of the rotor, then I can estimate the amount of material I will need and which type of crane I will need to assemble it. So the starting point is 15 megawatts. But I will just use this equation here, and I will shuffle it around with it. So what I'm looking for is the diameter of the rotor, or its radius, r. So we previously said that r, the radius, is hidden in the factor a. So on the right here, on the right hand side, I replace a by pr squared, and then I shuffle the equation around to isolate r. And then I simply replace all the variables with the input I have. So P is 15 megawatts, multiplied followed by 6 zeros. The air density is known. For the power coefficient, I will use 50% at first. It's typically the maximum efficiency a wind turbine, a real wind turbine can achieve. And for the wind speed, I will look at the average wind speed in the area. For this example, let's take 10 meters per second. Well, if you plug this into your calculator, you obtain a radius of 120 meters, which is equal to a diameter of 240 meters. Well, guess what? Last year, one of the main wind turbine manufacturers installed a prototype of a 15 megawatt wind turbine, which rotor diameter was 236 meters, very close to 240 meters. So now we know how to relate power to the size of a wind turbine. Which brings me to my conclusion. So floating offshore wind is the natural evolution of onshore and bottom fixed offshore wind. Its potential is enormous. It could cover up to 11 times our energy consumption. It will help us reduce our CO2 emissions and our exposition to volatile fuel prices. It will strengthen our energy autonomy, and it will improve our industry. I can't tell you if there is a size limit to those wind turbines, but I hope you're now able to estimate their size based on their power. Thank you for your attention. If there are any questions, I'm happy to take them.
Thank you so much, Johan, for a fascinating talk with a lot of detail, a lot of food for thought, especially as this project develop in and around Orkney. We have quite a lot of questions online already. Those of you who would still like to submit more questions, the links on the screen. And of course, if you're here in person, just raise your hand and we'll take your questions as well. But we should start with some of them online. A lot of them sort of circle around sustainability. So how much energy, how much material is actually required to make these wind turbines, and what can we do so that energy can be offset once the turbines are switched on? So how long would a turbine have to actually run to offset its own energy costs?
That's a difficult question. The lifetime span of a typical offshore wind turbine was 20 years. And now it has increased 30 to 35 years, so one wind turbine can have, let's say, 40 years. A floater will require approximately 3,000 to 4,000 tons of steel or 40,000 tons of concrete. The issue here is, I have not done personally the calculation to know how much carbon that emits. So I cannot really answer the question. My colleague who could answer that question.
That's the right one, but it's definitely something that's being considered. I think you already mentioned also about reducing the amount of material used for the blades themselves or for the turbines, but I've got colleagues that look even at blades that are made of fabric or things that and materials to actually reduce the material cost and of course also the weight, hence being more profitable.
Good.
Excellent. Right. So another very interesting question, which is to do with the floating in particular, which is to do with animals and mammals. We are well aware that, of course, the oil drilling in the North Sea has significantly disrupted and impacted marine wildlife, and there have been projects sort of investigating similar effects of fixed wind turbines. These structures seem to be a lot more lending themselves to be much less destructive, perhaps, of the marine wildlife. So, any thoughts on that?
Indeed. Floating offshore wind helps to reduce the impact on marine mammals and phanetic population, so everything which lives on the seabed. Why? Well, first of all, it's much faster to install a floating wind turbine. You just need to hook it up to the mooring lines and there you go. You don't have to hammer a pile into the ground or a big monopile into the ground. So you emit much more noise under water, which is beneficial for these marine mammals, especially. Secondly, you can, at the end of the life of a wind turbine, you can simply tow it back to shore. You don't leave anything on flanks. You can easily remove the anchors of the mooring lines, so you leave the site as it was before installing a wind turbine. And about the mooring footprint. So it's not true for all types of floating foundations, but it's especially true for the tension leg platform, the one you can see here. Because the mooring lines are vertical, the footprint of the structure is very reduced. It's not the mooring footprint of the mooring line system, is the same as the footprint of the structure itself. So by reducing the footprint of the mooring line, you reduce the impact on the benthic population. And also because the lines are straight, the mooring lines do not touch the seabed, so they don't rattle the sea ground. So it's in bed. Another aspect, but which is also true for fixed offshore wind, is that an offshore wind farm creates a sort of sanctuary for the marine mammals where they can escape fisheries or intensive fisheries and where they can reproduce and have enough time to grow and become adults. It's a sort of reserve effect.
Excellent. It's just clearly many advantages to them. Again, if anybody's got any questions in the room, happy to take those. There was an interesting suggestion online, would it be possible to actually combine some of the wave energy generation with the wind turbines, so effectively to create flexible structures that actually absorb some of that wave energy rather than try to counteract it with ballast or balance or tension?
Indeed. So there are many companies already looking into this very interesting solution. So you could indeed combine a wave energy converter system, so something that captures the energy in the waves, with a floating wind turbine. For instance, the TLP is very well adapted for this. TLP is a very stable structure, so you could put, for instance, a sort of system that would capture the energy of the waves, because the TLP doesn't move. It's a fixed point in which you could install a wave energy converter system. It's not ready yet for deployment. Let's first try to install floating wind turbines and make them work, and then we'll look into adding more energy converting systems on top of that.
Cool. So there's, again, there's a lot of questions around sort of weather and how do these things actually vary, and how does the adaptation of the various sort of grounding systems and the floating platforms vary depending on sort of weather. And are there any specific characteristics that, you know, are applicable to sort of ground workplace in the North Sea? We said that the North Sea already is good shallow depth, a relatively, you know, a very safe place to put a lot of wind turbines, but of course we're also looking towards the other coasts further out towards the Atlantic. So what are particular sort of weather considerations that need to be put in place so that you know, there's obviously different kinds of models that you describe.
Okay, so if the bathymetry enables it, so if I would have a site with the water that would exceed 200 meters, I would probably look into the spar type, which is very stable, it's very easy to measure. But I will also need to make sure that I have a harbour that is deep enough, typically a fjord in Norway, where I could build with structure. If it was on the west side of Scotland, I don't have access to those fjords, so I must first look into the TLP solution. Why? Because well, as I said previously, the TLP is a structure which is very transparent to the waves, to the loads of waves. And also in deeper water, because the lines are straight and not catenary lines, it needs less, shorter length of line, so you can potentially then save on the material costs there.
I think there's one kind of final point there. Let's see any comments in the buttons. Okay, right, we'll get to you in a second. I'll just add this final one and then we'll take some point for the audience as well. So there are still mooring lines though, and there's also the export cables that take the electricity to those subshore stations and then also onshore. What does that actually mean for, you know, post-traffic fisheries, you know, marine traffic, fishes, everything? So that basically means that when the fields of wind turbines are put in place, effectively you probably try to discourage people sailing through at all costs.
Indeed, so here we have to make a distinction between the unique TLP type and all the rest. All the rest use catenary lines, so I didn't mention it, but the radius of the distance between the floating platform and the anchor with a catenary line can reach easily 800 meters. So there's a large circle around a floating wind turbine that is not adapted for the trawlers, the trawling fisheries. However, with TLPs, it's a different world. There's nothing. The mooring footprint, as I said, is not larger than the foundation itself, so any boat or any trawling fish nets could easily pass next to the wind turbine without any danger. Maybe at the exception of the export cable. Not an expert in this, but the export cable would also probably not be too far away from the structure, so it wouldn't hinder.
Yeah, if somebody passes me a microphone soon, I'll be fine. Afternoon, everyone. My name's Nick Moore. I am the Marine Consents Manager for Thistle Wind. So, as part of our environmental impact assessment, we would have to assess the ground conditions of an export cable route. So, our perfect world situation is that we would be burying our export cables to protect them from, as you say, shipping, navigation, trawlers and the like. So ultimately, that's our sort of base case. Ultimately, if the geology from our offshore surveys comes back to say that it will be challenging to bury our export cables in areas sort of stiff clay and hard bedrock, we would typically spurtus lay them and then place rock over the top of them to protect them. So it still allows fishermen to come in and trawl close by. We still would prefer them not to trawl over the top, because of course there is always a chance ultimately if a cable is buried on day one, it doesn't stay buried forever, so we have to sort of continually monitor our cables to make sure they do remain buried and protected where possible, but ultimately sort of we endeavour to ensure that we don't impact other sea users as much as possible, or as little as possible, should I say.
I was just wondering, when it comes to the biggest wind turbines offshore on the west of Orkney, are the most they're going to be 100% finished before they put out to site? Or are they going to be constructed on site to some extent?
Sorry. For do you say west or east?
So are they constructed on, how much are they constructed on site? Or will they be just towed on from somewhere?
So here we have to make a distinction between the floating site and the fixed site. So take I will start with the bottom fixed site, because in the west of Argus there will be a wind farm bottom fixed foundation. So there they will first install fixed foundations, and wind turbines will be installed offshore. So they will install they will construct the tower section by section offshore. And at the end they will use a floating crane or a jack-up crane to install them as well. For floating sites on the east or the Orkney, it will be very different. The floating foundations will be assembled somewhere in Scotland. They could be towed to Scapa Bay, and in Scapa the floater will be placed somewhere in the bay, and we will integrate the towers in Scapa Bay, and then we will tow the full structure to the site. This is a big advantage of floating wind, is that you can integrate your turbine onshore, which is much cheaper, and then tow the whole structure offshore.
And thank you very, very much for all this exciting. Unfortunately, we're out of time, but I'm delighted. I mean, you guys are all staying here, right? You've got a stand just outside. So the Thistle Wind Partners, you can speak to them just outside the door, and I'm sure they'll be able to answer more questions and tell us more about the various projects that they're involved with. So for now, I'll just say thank you so much, everyone, for being here today. And of course, thank you, Johan.